Okay, so let's get started. Today's seminar, exploratory online seminar number 81. Today, I like to discuss correlation and causation. I'm sure like you have heard about this correlation and causation, or correlation is not equal causation, that kind of stuff. But what does that really supposed to mean? In the world of data science or statistics. So I like to kind of go through, what the correlation, what the causation, and what's the difference, how we can investigate the difference between those, and kind of like organize our thoughts, and then reach to the better conclusion. Okay, so let me introduce myself. My name is Kan Nishida, CEO at Exploratory. We started Exploratory 2016 to democratize data science. Since then, we've been building this tool called Exploratory, which is basically the desktop tool, but it provides a simple and modern UI to do all sorts of data science tasks. Our vision is the data-informed decision-making is essential to make the world better. Therefore, our mission is to democratize data science. Okay, so like I said before, the Exploratory is a modern and simple UI to do data access, data wrangling, visualization, analytics, and last not least, communication. These 5 things you can do. And then we are targeting not just for the experts, but also because we want to democratize, so anybody should be able to do through this UI. Okay, so that's about like introduction, and let's get into the main piece. So exploratory online seminar number 81, correlation and causation. Okay, okay. So let's so agenda is a correlation, and then I'm going to kind of touch upon a correlation first, and then correlation and causations. And then later on, like I like to go over like multivariate analysis and A/B tests by using the mask effectiveness study. Okay, so what the correlation? Correlation is, I'm sure like you have heard about it. So what you think correlation is the one like I want to talk about. But it's really the changes in one variable. In this case, one variable or one column or one attribute, whatever that could be. The one variable correspond to the changes in another variable with a certain regularity. And then typically, when you talk about the correlation, you use like a scatter plot kind of stuff, right? So like there's the x-axis and the y-axis, or horizontal axis and the vertical axis. And then you put the dots. Maybe dot can be a student, can be a customer, can be employee, whatever that could be. And then you see if there's any correlation. If there is correlation, then let's look at the most right-hand side chart. Something at the x-axis go up, and then it seems like the more higher it goes, the higher it goes. Also, the other variable side of the axis, which is the y-axis. Okay, so and then let's look at the most left-hand side, which is basically on the x-axis, the value goes up. Then seems like y-axis wise and value goes down. So it works in a kind of opposite way. However, it's important to note that there's some kind of regularity, some kind of rules that along with that, then like values actually move. So like it's kind of corresponding, right? So but the opposite of that is that the center, which is no correlation. So you have all the dots, and then you probably can't kind of figure out what is the best way to even draw the line, or to find the direction, which way it's moving. It's almost kind of chaotic. Why you have no idea where things are going, kind of stuff, right? So like by looking at the x-axis, then value, let's say, whatever that could be. Let's say like that's a years or something, like that age or something, and the y-axis is a salary or something. And then by just looking at that age, you have no idea what the salary could be. So there's no predictability, if you will. And then in the correlation, like usually like we use this thing called correlation efficient, or the sort of like a score, to indicate how strong or how weak that correlation is between the two variables. So typically ranges from -1 to 1. The 1 means the most strong, strongest positive correlation. And the -1 means the strongest but negative correlation. And the 0 is obviously the no correlation. Typically, the values can be between 0 and 1 or 0 and -1. But by using this, you can sort of like see that strengths of the correlation or correlational relationship. Okay, so why do we care about the correlation? Like I mentioned a little bit. Obviously, like you have the correlation relationship. Let's say we are looking at the time spent on the website. You have the website, right? And the customers come, and then like you want to see like how much this customer is going to spend or something. And for some reason, this orange dot is basically each customer or each website visitor. And for some reason, like you have this nice correlation between time spent on the website and sales or how much they spend on the website. Okay. Then maybe like you just draw the blue line kind of between, and then you can sort of like predict like how much this customer is going to spend or going to buy something, purchase, based on how much time this customer spent on the website, right? So what we are doing here is basically we're trying to predict, but also not even without the predicting, but we can explain how the sales works, because some customers spend like $5,000, how some customers spend $1,000. But if you find this kind of relationship, then you can now explain like how you can explain the variance of the sales. So basically, you kind of reduce the uncertainty, if you will. Okay, so you can explain or you can predict if you find this type of relationship, which is correlation here. Okay, and the correlation doesn't necessarily mean numerical, even though like you go to the textbook, probably it says that way. But how about like a categorical? Right? For example, you discount or not discount, or you go to the A school or B school or something like that. And then maybe in this case, the conversion rate has changed. One is 10%, another one is 20%. And obviously, it seems like when you do the discount, then you get the conversion rate of 20%, which is better than without the discount. So you can also, in this case, predict, or you can explain, right? So in a textbook wise, I think this type of relationship is called association, because one is a category and the other one is a numeric. But for the sake of simplicity, I'm gonna keep calling this a correlation. Basically, like there's a relationship between two variables. In this case, with or without discount, and then the conversion rate. Okay, and then I'm not going to go into too much detail on this correlation, but I have done the seminar in the past. So if you go to our homepage and then go to train seminar, and then in that page that there's a online seminar section, if you click it, then you can go to the past recorded seminars. One of them is called correlation and association. Okay, and actually, like, I'm gonna go to exploratory and see what the correlation, how you can work with the correlation quickly. So this is the HR employee attrition data. Okay, and then here's a summary view, and we have 1,470 rows. That means 1,470 employee, because this data, that each row represents each employee. Okay, and when I go back to the summary, and then there's a correlate button. This is the best way, or the most simplest way to investigate the correlation. So at the column, like what I want to find out, so there is something called monthly income. Let's call it this like income or salary, okay? And then there's a variance between 1,000 and 20,000 as almost. So what makes this difference? Is that because coming from people overtime or working overtime or not overtime? Or maybe because of the gender is like a male and female gap, or maybe some kind of education level that makes that difference. Okay, so in that case, I'm going to select the what I want to know, or like I'm interested in. So in this case, monthly income. And then now at this point, the summary view, the correlation model, investigate the correlation or the relationship between all the columns against monthly income. Okay, so the first one we are looking at is basically here, age, and the x-axis is the age. And then in this case, age is numerical, so that's why it's actually divided in 10 groups with equal width. So, and each section, let's say in this case, 18 to 22.2. And then there are, number of rows says 57. So there are 57 employees. And then calculate the mean of the monthly income, which is 2,427. It does the same thing for the each section, and then draw the line. Okay, so by looking at this line, obviously, like, okay, so the older the age and the higher the monthly income. Okay, and then you can actually sort these columns based on the strengths of correlation. There is a correlation, for example, here the correlation bracket Pearson, but I recommend R squared to sort them because correlation it can be calculated only for the numerical variables. That means, for example, something like here, attrition or business travel cannot be calculated. Okay, but R square can be calculated by building the linear regression model behind the scene and then calculate the R square. So anyway, and also even the numerical values, numerical variable, basically in this particular scenario, which is so-called univariate or like simple regression model in a way, so like only monthly and income and age, in that case, R square is actually the square of correlation. That's why it's called R square, because we often call R for the correlation. Okay, so having said that, we can use R square to sort all the columns based on the strengths of the correlations against monthly income. Okay, so now what we are looking at here is basically like a job level has the strongest relationship with monthly income. It's kind of obvious or of course kind of thing, right? So, but nonetheless, so here the correlation is 0.95 and the R square is 0.90. It's almost like if you know the job level, you know the monthly income. Probably this company is inside monthly income based on job level. So it's not really useful information, but nonetheless, we have that. And here's the job role. Some of the job role has higher incomes than the other income. That's also kind of typical. And the working years and age and attrition and so on. Okay, so you can find the correlation this way. And another one you can actually do is, for example, in this case, a monthly income. There's another one, a column called attrition. Attrition meaning that if this employee has left the company or not, or still stay in the company or not, or stay in the company. Okay, in that case, we can also find the correlation. Okay, so if I select the attritions, in this case, now the not numeric, it's actually logical. And then, but again, to do the same thing, like it's try to investigate the relationship between all these columns against attrition. And then I'm gonna use this AUC, which is sort of like R square, except this indicates the strengths of the relationship or correlated relationship against attrition. Attrition is a true or false. Okay, so it's not numeric. It's almost like a categorical, but happen to have only two values, like true or false. And in that case, you want to use AUC that gives you the idea of the strengths of the relationship. AUC case ranges from 0.5 to 1. 0.5 is the weakest and 1 is the strongest. Okay, so it looks like, again, the job role has relatively, not like super strong, but relatively compared to others, stronger relationship with attrition and total working years, monthly income, overtime, and so on. Okay, so we can find this type of relationship very quickly, but then today's topic is that correlation is not equal causation, right? So let's take a look at this chart. This is like a Japanese cars sold versus suicides by car crashing. Okay, and then when we look at this one, this is a kind of time axis, so you got to be careful for the other reasons. But nonetheless, looks like super correlated. I mean, like, when the Japanese, more cars sold and then more suicides and then like less cars sold and then less suicides. So you know what? Let's stop importing Japanese cars. This is very dangerous, right? So if you are working at American companies, you might want to use this chart. And then another one is the divorce rate in May in the United States versus margarine consumption. And when you look at this chart, wow, this is a strong relationship again. So you know what, like we don't want to, we want to improve the married life in this state called Maine. So let's ban margarine in that state. You know what? Like this is not actually a good idea for giving the margarine in the state, right? So of course you're not going to do it. You sort of like, yeah, maybe like that just happened to be. Yes, that's the kind of thing that we gotta be careful. This is another example. Ice cream sold and then shark attacks. Both of them increased from May, June, July. And obviously, when you look at this chart, you're like, yeah, so what? I mean, it's just a fake correlation, right? I mean, like it's correlation. It is correlation. It's not fake. It is, but that doesn't mean causation, right? That because it's not that the more people buying ice cream, the more people getting attacked by shark because the shark loves vanilla or chocolate, taste in the ice cream that's being consumed by people. And also that the more people getting attacked by shark, and then people feel like, wow, it's kind of scary, like I want to eat ice cream. There's no such thing. Maybe some people. Okay, so it turned out like there's something called confounding factor, which is this case a temperature. So temperature goes up, then the more people go to the ocean. So therefore, more chance to get attacked by the shark. And also, obviously, the temperature goes up, then we want to eat ice cream, right? So sometimes there is this type of the confounding effect that we don't see when we are just so focused on between shark and ice cream. And when you look at the chart or you look at the data, then it's almost like, well, maybe it goes, like ice cream, the more ice cream sold, that's why the more shark attacks. I mean, in this case, probably you're not going to think that way, but sometimes. So that in real world, when you see something like that, you're like, yeah, that's so stupid. But in the real world, we see this kind of confusion all the time. So here's an example. This is Jordan Peterson. He's an author and also I think a professor at this university in Canada, and he's a very interesting person and a great person. And it's sometimes like for some reason in this country, United States, he's a controversial. But from where I'm coming from, I really think he's a great guy. But nonetheless, he was invited to BBC and had a very heated debate between the anchor woman and then him. And you can watch on the YouTube. So I strongly recommend you take a look. It's very interesting conversation or debate. But anyway, the whole point, one of the topic in that 30-minute interview was the gender gap in terms of the salary. Okay, so she was claiming that like the company she works at the BBC, there's I think that was a BBC, not the general in the United Kingdom, but there was a difference between male and female in terms of median salary, and they found that like 9% difference. And this makes her upset that there is a difference or gap between man and woman. And then, but somehow he has a background in social science, and also he's a psychologist as well on the clinical, psychological clinical doctor, I think. But anyway, so he's pretty good at the statistical analysis. So he obviously has done that kind of research before. So so he's basically telling her that there's no, it's not because of the gender gap. There's something else, and then so there's a debate. So he was saying like basically there's a difference, but that doesn't mean that the difference is coming from the difference of the gender. In the world of social science, that we use multivariate analysis rather than univariate. Okay, so here is the this topic that I want to talk about. So just bear with me if you are not familiar with multivariate analysis. If you're already familiar with it, just let's go along with it. So there are other reasons. There can be other reasons, right? So not just the gender, but also there may be occupation difference, maybe interests are different, personality traits are different. So we have to look all other things. And so, and then she said, like, why do we women need to put up with those multiple reasons? I mean, like, why? Well, Jordan Peterson was like, you don't need to put up with them. I mean, it's not like I'm asking you to put up with them, but it's important to understand what is causing that gap. But from that anchor woman's point of view, she could see only this kind of chart. There was a 9% difference between a man and a woman. So just look at the chart, there's a causal relationship. No, that's not the causal relationship, that's a correlation. I don't think they said exactly the causal relationship or the correlation. This particular part I edited, but what basically there's a confusion between, there's a confusion, I think, on the anchor woman's part. So therefore, the conversation or the debate was not really having a dialogue. It's almost like going parallel, and that's because of this difference. So the Peterson says, if you do multivariate analysis, some personalities like agreeable as a personality or character influences the salary difference. That actually can explain some part of the difference, not all of them, but some part. And then the woman says, I don't care about multivariate analysis. What the hell is that? Well, 9% gap exists. I mean, don't you think that's not fair? And from Jordan's point of view, well, it depends why it's happening. So women tend to be more agreeable than men, and then that has more to do with the fact that women's salary tend to be lower. But not all women are agreeable. I'm certainly not. And then according to Jordan Peterson, well, I'm not trying to generalize, but that's because even the job between the jobs are different. So for example, in the doctors, women tend to have higher salary than the men. So it's not, just because of man and women. So the anchor woman said, like, you deny there's a gap between man and woman for salary. And then Peterson said, I don't deny that there's a gap. I deny that there is a gap because of the gender. So this conversation, when you're listening, it's interesting because if you understand this sort of like correlation causation difference, or even like a multivariate analysis, you can see where Jordan Peterson is coming from. But if you're not familiar with these concepts, then you sort of like get kind of confused, or you think it's like Peterson was not really trying to accept the fact that there's 9% gap. So it's very important to understand this correlation and causation, not just in the statistical analysis class, or not just in the workplace, but in general. We live in the world that these two things getting confused all the time. And then just to tell you that it's not because these anchor women were ignorant. It's actually the people who teaches this causation or causal inference makes this mistake all the time. I've been seeing in real life. So it's not like because of that some people better at this than others. It's just that we as a human being are not, I don't think we are not that good at differentiate between these two. So we always have to be humble and ask questions and then try to dig through between these things. Okay, so what the hell is multivariate analysis, right? So let's look at that same chart, the median salary, the comparison between male and female, and then it turned out there's a 9% difference. Okay, so the one question is this 9% difference is significant or not? That's the statistical analysis question. But let's say this is significant, meaningful difference. Then, okay, so there's a correlation between gender and salary. Male has higher salary, female has lower salary. But as Jordan Peterson said, agreeability has also some role in that salary. Okay, so I got the chart here, and then left-hand side, the not agreeable people, and then right-hand side, agreeable people. And maybe there are some men are more agreeable than the other men, and the same thing, some women are not agreeable at all compared to other people. So maybe in this each box, each like a purple and a green, there might be like more men and women kind of mixed together. But here is we're just comparing the personality trait. Okay. And then there is whoa, seems like 9%, 10%, whatever the difference is, it seems like a difference. And then again, let's assume that difference is a significant difference or meaningful difference. Then we can say, okay, you know what? Gender and salary seems to have some kind of relationship, but also this agreeability trait also has a relationship between, to the salary. So salary and agreeable has a correlation. Okay, so let's go back to look at this not agreeable chart. Okay, and then what's we're missing is like the male female information. So I'm gonna bring that information here, and then it turned out some female are agreeable, but also not agreeable, and some male are not agreeable, but also they are agreeable male as well. Okay, and then so this one is like more people in the non-agreeable than agreeable in total. So we are not sure like which has more female or male kind of stuff. So like I'm gonna just convert the ratio so that we can compare in a sense that like, hey, it looks like a more female are agreeable than non-agreeable. So for example, in the agreeable box, like more female there. If they're male, but tend to have more female there. So looks like by looking at this chart, what we can tell is that it seems like a gender and this agreeable personal trait are correlated, meaning if you the woman then tend to be more agreeable than non-agreeable. It's not 100% black and white, but just more like a kind of tendency, right? So here we can draw this kind of triangle here, and then there's a line between now agreeable and gender. There is a correlation here as well. Okay, so it seems like there's a triangle relationship, like all correlations everywhere. So then the problem is now going back to the debate that is the gender is the one that causing salary, gap, or agreeability is the one causing the salary gap. So maybe, as Peterson said, so agreeability is the one playing the key role, right? So if that's the case, obviously agreeable and the salary has a correlation. If you look at the bar chart or whatever the way you visualize it, there's a relationship there. But because agreeable and gender has a correlated relationship, so therefore the more agreeable people, so that means the gender is woman, and then the more agreeable people and the salary is higher, and then the salary is lower. So therefore the woman's salary is lower. So it's agreeability is the one's kind of driver. But if you're looking at focusing on only the gender and the salary, looks like the gender and the salary has a direct relationship. Or the other case is that, yeah, actually the anchor woman was right. Actually, gender is the one is causing that salary. Then, woman is more agreeable. So it happened to be like agreeable people have less salary or lower salary. So we get kind of confused, right? So which one? Like which one is causing the salary gap and salary higher or lower? And then one way to address this problem is that, or one way or multivariate way is that, why don't we just hold one variable constant? Meaning, okay, let's just limit only the male. Let's take a look at the male data. Okay, and then in that group, in that cluster, then there are some people are more agreeable, some people are less agreeable. And then if we see that change when we see the change in agreeable, and then do we see the change in the salary? Meaning, do we see the correlation between agreeable and salary in this male data? We can do the same thing for the female. if all the data is female, all the employees are female, and then if some of the women are more agreeable than the other, do we see the correlation between salary and agreeable? If we see, then agreeable and salary has a relationship. And we can do the opposite. So the agreeable, we hold it constant. Let's say, maybe like, I don't know, whatever the score 1 to 5, and only the 5 people, only the 3 people, whatever that could be, just one group. And then in that particular group, let's say like agreeable 5, then there are some women, there are some men. And then do we see the difference in salary between the male and female? And if we see it, that means, okay, there is a difference, maybe brought by the gender, right? So at least we can kind of like organize it. And then, but this is a triangle. So what if like there are other reasons? Maybe like, even like, agreeable doesn't matter, but then maybe could be some other personal trait. Yeah, could be. But just let's focus on these 3 things. There's only agreeable, gender, and salary. At least we can say what is not really having a relationship or not. Maybe something else could be, but at least like we can kind of like organize what are the candidates that have relationship with salary. Okay, so that's where the multivariate analysis comes in, and it's really the statistical model. So in the machine learning world or statistical learning model, like this sort of like prediction, the world of prediction model, there's one is a statistical and the other one is just machine learning. So statistical side, there's something called linear regression, logistic regression, Cox regression, that type of the algorithms or models, if you will. And then the other side is like a decision tree or random forest and XGBoost and all those machine learning side of things. But statistical model can help you to analyze just that multivariate analysis by basically you're not going to be doing this manually, but actually the model itself come up with the model or whatever the formula or whatever the insights that will give you the tool to answer the question of what if I hold constant of other variables, and then what happens when the value changing, for example, gender and the salary changes or not. So I'm going to take a look at I'm going to use a linear regression model, but if you're interested in linear regression, I have done the seminar in the past. So like the same thing, go to the seminar page, and then you can find online seminar 14. This one was done in 2019, so they were pretty old. So, but I think you get basic of the linear regression. But here, I'm going to again use exploratory here. And then what I want to know is the monthly income will be caused by, which we call it, the gender or not, right? So like I'm going to go back to monthly income as a target variable. Okay, and then I'm going to sort it. Okay, so now it's a job level is obviously, but and then job role and so on. And here the gender, I've already found here is that there's a difference. Like a female is average is $6,686, and a male is $6,380. So they're about like $300 difference or so. And then by looking at this, it's actually important thing here is something called p-value. That's 0.0884. That means like it's like a 8%, 8.84%. What that means. So basically, this is something called a statistical test. And then typically, like if you have this value to be like close to 0, that means there is a statistical significant difference. But when you look at here, is basically like looking at the kind of confidence interval. You're comparing these two, and what it is here is if this confidence interval is overlapping, that means because this confidence interval is a 95% confidence interval. That means the true value, which is in this case the mean of the female, should reside within this area. So we don't know like this particular data we know, right? Like out of this 588 people, we know exactly what the mean of the salary or the monthly income. However, we might not have like all the employee data here, or we might have like more people coming in tomorrow or a month later, whatever. So we, instead of like a data summarize value about this particular data set, we want to see more including others and that might not be here or might be coming future, or maybe happen to be in the past or whatever stuff, right? So that's where the confidence interval comes in. So the true value can be around here. It's more like kind of error, right? And the male is also, so it can be the same because the confidence interval is overlapping, right? So therefore, like we can't really say there's a statistical this significant difference between these two. So at this point, our job is done already in a way. It's like, hey, you know what? Like we can't really conclude just because there's $300 difference. The female salary is higher than the man or something. We can't conclude that way statistically. But let's assume, but still we don't know, right? So like maybe let's assume like there's a difference. In this case, not, but let's assume. Or for example, in the job role, it looks like there's a difference between among the job roles. So manager and the research director has higher salary or no. But maybe that's because the total working years is different. Maybe these particular jobs are like happen to be the older people. Look at this age. Like older people have higher salary. So that's, maybe the job role. Look at this manager. Maybe in this company, only the old people can become managers. So it's not really the job role, it's actually the age. So we want to actually clarify this. We want to organize, what's going on, what variables actually have the direct relationship or with monthly income. Okay, so in that case, you can go to the analytics view and create a linear regression in this case, or you can create a linear regression from here. I am going to select all these columns. I excluded job level because job level is kind of like obvious. It's almost like, it's like, job level monthly income. I don't know, like it's it's sort of like maybe because of that job role, because of the age, total working years, and then job level will be decided based on the total working years, and then because of that, the monthly income be decided. So I exclude that one. But among these, maybe some of the staff have the relationship with the monthly income. And then so let's take a look at that one. And then I'm gonna just from the column header menu and create a linear regression. And here it is. So I'm not going to go into the detail, but a key thing here is what are the most important element. One thing I need to be careful here is something called multicollinearity. And then if you see any bars beyond 10, that's a threshold. That means there's something among the variables have this too strong relationship with each other. In this case, department and job role, this is actually the hierarchical relationship, meaning, for example, some of the job role, maybe research director is under the R&D department. Some of the job role, the sales executive is under the sales department. So it's sort of like similar information. So I need to exclude one of them, department or a job role in this case. And then what you want to do is you want to take one by one. So I'm going to take department off and then keep the job role instead. And then click run. And you want to repeat this process until like you don't have this multicollinearity problem or greater than 10 variable. So in this case, no. So like it's good to go. So like when I go to the importance, then you can see which variables are more important in terms of like predicting what the monthly income will be. Then it seems like a job role plays a huge role, and the total working years is also. And for that, after that, almost like an age or education level and gender doesn't matter. If you want to really do more like a statistical analysis, then you can go here. When you see the gray variable, that means those are not significant. So therefore, those don't have the relationship with monthly income. But here is one thing. In order to understand, for example, here, let's look at total working years. in order to understand this one, it's basically the 1 year increase in total working years have two, the second from the top, it says coefficient 206. This is $206. Okay, so the 1 year increase in total working years, you can expect $206 in the monthly income, which is basically this blue line. Okay, the 1 year increase is a slope is a $206. When all other variables are constant, meaning same job roles, same age, same attrition, same education field, all the other things are the same, then you can expect $206 increase. Okay, so because that's how you can understand it, therefore, basically what we're doing is, remember the triangle chart? One, you want to hold a constant for the one variable, then see like if there's still the relationship between the rest, right? Rest two circles. So that's exactly what we are doing here. For example, look at the gender. Okay, and then when I go to the coefficient, gender is gray. And then female, and then base level is male. So like compared to male, the female salary is actually minus $167 when other variables are constant. However, this minus $167 is almost like not a meaningful difference. It can be explained by just a random variance. So therefore, from statistical point of view, this is not significant. That's why it's gray. Then we can kind of organize, okay, what are the things that actually have relationships with monthly income? So the insight you can get out of here is different from the summary views correlation mode. Okay, so for example, age here looks like, okay, there's a correlation of 0.5. But if the other variables are the same, let's say constant, meaning the job role, the same job, same working years, then the age actually doesn't matter. It's age and total working years is kind of same, but some people join the company from, after 30 years or 40 years old. So that has more impact on the monthly income than the age itself. Okay, so this is basically what we've been doing is multivariate analysis. And when you go through something like this, then obviously the answer can be more complicated than the simple bar chart and simple answer based on the bar chart. So that's why it's important to do the multivariate analysis. But you ask, how about other variables? Because you had only like 20 columns, 20 variables, or I forgot how many columns, right? What if like how many times you call with a boss, how many times you go out with a party with your boss, and doesn't that count? Yes, could be, right? So only the data we capture in this data are always limited. So then maybe we can't really conclude a causation because what if like a confounder element or variable is actually outside of the data you have? So that's where like there's this A/B test or RCT. In a science world, we call it RCT, randomized controlled trial. Web or tech companies or, SaaS, subscription business in that world, we call it A/B test. Basically the same thing. Here's a Netflix CEO's comment. I think he just maybe just took off. I forgot. But anyway, so Reed Hastings used to say, leaders like Steve Jobs have a sense of style and what customers seek, but I don't. So therefore, we need consumer science to get there. And what that consumer science really means is that like a former VP of product at Netflix said, over the years, my focus shifted from what do customers say to the let's test it mentality of consumer science. So that's what really the consumer science, which is basically let's test it. So what the test means is that hey, we are discussing about what should we do about the the color of the button, for example. Maybe the button, some people say the pink color is extra, take the attention, so therefore it makes people click on the button or something like that. Should we change it or not, right? So instead of keep talking, keep guessing, let's test it. Let's create two versions. One is the original, one is the changed version. So for example, originally, like we had a blue color on the button, and then let's change to the orange. Maybe that might increase What do you want to increase? Well, in this case, we want to increase the conversion rate or something, right? So we create two groups, and then one assigned to the A version, and the other one assigned to B version. But here we have to be careful because the same thing can happen with a problem of multivariate analysis or limitation of multivariate analysis. What if like you thought those two groups are the kind of same, but are actually different? Maybe like one group actually have more purple people than the other group, whatever the purple really mean. But maybe there's some kind of characteristics or the attributes are different. So therefore, when the people come to website and then you just randomly split and then create two groups, and then because you randomly select them and then split them. So therefore, should be in the average, it should be like kind of the same people. Individual can be different, but as a group, more or less the same type of people. So they're then assigned to the page A and page B. And then we observe which page perform better. And then so like one is A and B, and if the A performs better, like we can conclude that like, okay, like maybe like orange button works better than the blue button. Our CT world, randomized control trial, we call it treatment group and control group. Okay, so I want to use a mask wearing example here because that's what happened. That was like one of the most important thing was happening in terms of the RCT. So the beginning of the 2020, I mean like 2020, beginning of this whole pandemic, COVID pandemic, right? So United States had a lot of like confirmed cases or infected or test positive, whatever you call it. And Japan was super low. And then basically New York Times says, or many media said, oh, hey, maybe because of the mask. This was a really way early around the April or May time, right? And then basically, like when you look at here, okay, so maybe because Japanese wear mask and American don't wear, so like maybe we should wear mask in the United States, and maybe all over the world. So what happened is Japan. So I'm gonna just kind of expand this. Like Japan had a very beginning is a very few cases. So I'm gonna just expand it just for the Japan, exclude the United States, right? And then that article at the New York Times was actually June. And then look at this data. And then, hey, see, like maybe the mask actually helps. We should do a mask. And after that, what happened was like the number of the cases started increasing in August in 2020, just 2 months later. And then as the day goes by, and then by the end of the year, the number of the cases kept going up. And then the next year, 2021, September, even like way higher. And then 2022 February, even like what was going? It's like hit the record high. And then last winter, December, I mean last December, was like another like a huge wave was coming. Okay, so and then when I went to Japan December 2022, and the kid is basically 100% people wearing masks, even when they walk by themselves and by alone at the nighttime or outside, whatever. Like 100% people wearing masks. Maybe like you can say 99%, 99.9% or something like that, but it's close to 100%. I was the only one who was not wearing mask. So then, when you look at this chart, is that mask really working? If it's 100%, like these 3 years, 100% people wearing masks. They didn't stop wearing masks, but the number of the cases kept going up. And like, what was going on? And then when you go back to the Japan and the United States, at the beginning, Japan was lower in terms of cases. Now it's actually higher. If we focus on only the 2022 part, then Japan is actually obviously higher. So when you look at this chart, it's almost like you want to say the opposite. Maybe like the mask is the one who's actually causing the more cases, right? So the question is here is does mask work? Obviously, by looking at those charts, you can conclude you can conclude the mask doesn't work, but that's not really scientific, isn't it? So here, somebody said, let's test it. And then at the very beginning of the COVID, like 2020, there was a huge test happening in Denmark. They literally tested for this COVID-2, like see, like, hey, it can prevent COVID-2 or COVID-19, sorry, infection. So what they did was like created two groups and asked one group to wear a mask, asked one group to not wear a mask. And then they randomly split two groups and then make that difference. When you have two groups, make sure there is some kind of, there's no bias, right? There's no skew. So they look at it, like what kind of occupations they have, where they're coming from, or what kind of thing, do they smoke or not, like, what the gender, pretty much the same. There's a slight difference, but pretty much the same. So because they randomly split. And then they tested it about like 2 months or so. And then see at the end, they see how many people got infected. And the people who are not wearing mask group is 2.1%. The people who wearing mask is 1.8%. Then what they did was like basically with that result, they applied a chi-square statistical or hypothesis test. Okay, because just because this is a 2.1%, 1.8% difference, does that mean there's a difference between these two, right? So because it seems like they're only like 0.3%. Is that difference is significant or not? That's the very important point. And they decided that p-value is 0.05 or 5%. And then they calculated the sample size, how many people they need to have, so that's enough for them to conclude whatever the conclusion. Okay, so basically, like at that time, the 2% of the people were infected, so infection rate was 2%. So therefore, they want to find at least half of that. Like if they can half that, maybe from 2% to 1%, then that's a meaningful difference. So in order to have that difference, observe the difference, how many people they have to bring in, then they estimated 4,636 people. Okay, to have the 80% power, the significant level of 5%. Those are kind of detail to, so I'm gonna skip that. And then at the end, maybe because of drop rate, so like they ended up like recruited 6,000 people, created two groups, and the 4,862 people actually completed the study. And then then they got was basically 42 people infected in the group with mask, and the 53 people got infected in the group from the group of not wearing mask. So by just looking at this, then you calculate 1.8%, 2.1%. But remember, they wanted to see like 1% difference because from 2% to 1%, so this 0.3% is significant or not. Obviously, that is too small. So because that value itself here is minus 0.3%. But when you consider the confidence interval, then minus 1.2 to 0.4. That means the true value is somewhere between 1.2, minus 1.2 to 0.4. It can be minus 0.3. It can be minus 1. It can be 0.3. It can be 0. So it's they're not sure if that is enough to say which one is better than the other. So that's basically like they're saying it's not statistically significant. And when they calculate the p-value, which is 0.38, 38%. So 38% chance that this kind of thing can happen, even from the same group, even from like, let's say like everybody wearing mask, but you create two groups and everybody wearing mask, then you're going to see this kind of difference, like minus 0.3%, as 40% of the chance or 38% of the chance. Opposite to, like if you have like all the people who are not wearing masks and then two groups, and then you're going to have this kind of difference. So therefore, they conclude it's not statistically different. Okay, so that turned out that was not the only test. I mean, in the past, even before COVID, there's a bunch of tests for the mask efficient, mask effect. and then posted on the WHO website, and every single test basically no significant reduction. So it's kind of known for it. And then there was still some people asking like, how about COVID? COVID is different from any other virus, but it turned out basically the same. So Cochrane Library, I'm not sure that you have heard of it. This organization does really prestige in terms of like this type of meta-analysis or evidence-based research. And they actually took up like 67 studies back in 2020, and then they conclude the same. Basically, there's not much of a difference. But they republish a new study just came out end of last month, and then they added like extra 11 RCT, randomized control trial from all over the world, including the one from Denmark, the one that I just showed you. And then they researched again, and then at the end, they basically conclusion was that probably makes little or no difference in how many people have flu, COVID confounded by laboratory tests. This is between the mask wearing and non-mask wearing. And they even checked the N95 compared to regular mask or surgical mask. And then there again, there's not much statistical difference. So with the time is limiting now, it's almost like the end of the time. So I'm going to kind of go skip it. This one chart is actually interesting. Here is all the tests, all the study done all over the world, and they collected. And then every single test they're looking at is basically the most right-hand side is a risk ratio. Risk ratio is one is, for example, this one is wearing mask, is not wearing no mask is the right-hand side, and not wearing mask left-hand side. So which one has more risk than the other? So the wearing mask should have the lower risk than the no mask, right? So like the dot should be on the left-hand side, but when you have the confidence interval, it's all on the center line, which is a 1. That means one is here. So that means either way, it's basically there's not much of a difference. If it goes to 5 or something, then 5 times this one has a less risk on something. So, but it's actually it can be 1. So therefore, there's not much difference. So what I'm trying to say here is that just because you see the correlation or some kind of association in a chart, that doesn't necessarily mean the causation, right? So because of this kind of situation, so ice cream sold and shark attack and stuff. But then what we can do, then you can do 2 things. One is multivariate analysis with statistical model. At least you can hold other variable constant. Then you can see that one variable change can happen at the same time the target variable change or not. And then what's the difference? So you can sort of like clarify or organize, the relationship among or between the variables. So that's if you have only the sort of like observational data or whatever the data you have, then you can at least do this to sort of like organize your hypothesis or whatever the relationship you are thinking. But ideally, you want to do the A/B test or RCT like we saw, but it's not. Then that way, like you can really get rid of the potential of having the confounder in one group or the other. Then that's actually a better way to sort of like analyze or investigate the causal relationship. But not every data, not every stuff we have in this world can be tested like A/B test or RCT. So sometimes we have to actually do a multivariate test. But still better than just looking at a bar chart or just a line chart and conclude simply. And then surprise or not, but in the world, like I said at the beginning, even the people who teaches causal inference, they are super opinionated on this like a causation and correlation, but it comes to in their daily life and they make the comments happen, ignoring the fact that the correlation is not causation. Okay, and one thing though, like I have actually skipped one thing here is like that Chi-square test is the one used in the mask study. So in exploratory case, you can do the Chi-square test as well. So let's look at that. For example, there's attrition, right? So like let's say, like, is there attrition difference between men and women? So in that case, go here, statistical test, and then Chi-square test. And the target variable in this case, I'm going to select attrition. Okay. And then what can make the difference between true and false? Maybe like how about the gender? And if I run it, and then you can see the statistical test. The way to look at here is the p-value is 0.25, and that's too big. Depends on like what the threshold, but typically it's like 5%, which means 0.05. And then, so this is like 25%. So that means even with the same group, let's say like, maybe like all the female group, but if we randomly select, split into two groups, this kind of difference can happen as a 25% of the chance. Okay, so that means it's not really that because of the gender, maybe something else, just a randomness. Okay, so but in the data though, if you go to ratio, and if I just select the true, that means male has 17% of attrition rate compared to female, which is 14.8 or 15%. So almost like a 2% plus like few 2.2% difference. So the question is always like that kind of difference, just because you see the difference, does that mean something that you should really care about? In this case, or it's not. So you can't really conclude there's a difference between them. And there is a difference in this data, 1,470 people's data. But if you want to theorize what is actually causing, then like, you got to be strict about the amount of the difference that is significant or not. Okay. All right, so that's it. I think it's a time, so I'm going to end it here. Thank you so much for joining today's seminar. And as always, go to our website and then go to the online seminar page. We have future seminars lined up, even from next week as well. And then also all the seminars are recorded and published on the YouTube. So please take a look. And also don't forget, go to the how-to page and see the tutorials and the videos to see like how to use exploratory. And then my information is here. So if you have any question, please feel free to reach out anytime. And then please follow Exploratory Data at Twitter. So again, thank you so much for joining real time. And then please stay tuned for the next week's seminar. Okay, bye. Have a great rest of the day.